So next talks by Professor Makhlouf that will continue the course about algebraic deformations. So please, Professor.
Okay, thank you very much. Okay, let's continue. In fact, finally, we are ready to define formal deformations of algebraic structures. Deformations. I will do it for associative algebra, but it will be the same for any other structure of associative algebra. And this is this was the first type of algebra considered with this approach by, as I said already, by Gerstenhaber. This was in 1964, after one preparation paper about homological algebra. And this was about associative algebra. This was for associative algebra and rings. And it was extended later by Nienhuis and Richardson. In 1967 to Lie algebra. And my colleague Friedrich Weigmann will talk about the deformations of Lie algebra next week, I think. As I said, this was based on this formal power series. And now let us start by considering an associative algebra A. This is our vector space, and mu the multiplication. This is an associative algebra. Yesterday, we have seen that that if let us consider that A is a K vector space. The main idea here was to extend this base field K to KT, to KT formal power series. With parameter T here. And yesterday we have seen that we can also extend any vector space to its corresponding formal space, AT here, then formal power space, so series space. And now what we call a deformation of this associative algebra, then a deformation of a formal associative or a formal deformation, let us state it as a definition. A formal one parameter deformation of an associative algebra A. Let us denote it by mu0. Let us denote the multiplication by mu0. Here, I recall you that mu0, this is a map from A tensor A or A times A to A. Then this formal deformation is given by one parameter family of multiplications mu t, and this mu t is defined as a sum of t to I mu I here, running from 0 to infinity, such that mu I are bilinear maps from A tensor A or A times A to A, and mu t and mu t satisfies the associativity condition. Which means that mu t of x, y, yes, I should say, and mu t is kt linear, is kt linear, and mu t satisfies the associativity conditions, which means that mu of mu t x, y, z, this minus mu t of x, mu t of y, z, this is 0 for any x, y, z in A. Okay, then this is the definition. Then in fact, now if you want to deform a structure, you have just to consider a family of the operations with respect to a parameter t here, and this family of family mu t, this formal deformation, this mu t is what we call a formal deformation of mu 0, because here you can see that if I set t to be 0, then mu t is mu 0. Then remark here. Then if t is 0, then ut equals mu 0. I mean, the original operation of your algebraic structure. Okay. And now, when you have this family of operations or multiplications, of course you have to fulfill the conditions of your algebraic structure. Here we are dealing with associative algebra, then with this new operation defined with respect to t, it should satisfy the associativity condition. And of course, if we deal with Lie algebra, then this mu t should be skew symmetric and satisfy the Jacobi condition. Okay, and if you look at the condition, I wrote it only for elements of A. Of course, in fact, when we are here, if I want to write the new operation or the new algebra, I should say that the new algebra is the new algebra. It is defined, in fact, by the formal space AT and the multiplication mu t, and this is over this mu t is associative over AT. But since we are assuming that mu t is kt linear, then it's not needed to check the associativity on all elements of AT, but it's enough to check it only on elements of A. And this also will be the situation for as soon as you have this kt linearity, you can and also homogeneous element, then or relations. It could be more complicated, but then it's enough to consider this new multiplication satisfying only elements, fulfilled only for elements of A. Okay, is it clear? That now this, of course, we have here many unknowns. Then if I rewrite this mu t, then this mu t, as I told you, this is mu 0 plus t mu 1 plus t squared mu 2, etc. Okay. Then of course all these mu 1, mu 2, mu 3, etc. are not fixed yet, and what we want is to fix them. In order to get this this condition, which is denoted by star, satisfied. And this star equation is called the deformation equation. We have to solve somehow this this equation star and get solutions on these mu i's to the satisfying this star equation in order to obtain a deformation of our original operation, which is mu 0 here. Okay. Now let us try to solve this equation. Then this is called a deformation equation. This is deformation equation. Okay, then we have seen, we have fixed this mu t to be a sum, an infinite sum. Let us replace and try to solve this equation step by step. Okay, first of all, let us replace this mu t by its expression in terms of t. And then okay, then what will become this star equation? Then star is equivalent to what? Then it is equivalent to the sum of t to I mu I, sum over I, running from 0 to infinity, of, again here, a sum of j from 0 to infinity of tj mu j x y z minus mu, a sum again here, a sum, can use the same here, t to I mu I of x, a sum here I from 0 to infinity, here from g 0 to infinity, t to j mu j y z, and this should be equal to 0. Okay. Then now we try to we use the linearity and try to rewrite this equation by putting together all the t's. Then what we will have here, it's a double sum now, I from 0 to infinity, sum from j from 0 to infinity of t to I plus j of mu I of mu j x y z. I can write it like this: mu I of x mu j of y z, and this should be 0. Okay. And if I can rewrite it again here, maybe by putting this I plus j equals to some p. Oops. Then we can set I plus j equals p. I change these indices. And then what I get here is a sum, again a sum of, in fact, what I want to have here is T to P, and here it becomes mu of I, mu I, and here mu P minus I of X, Y, Z minus mu I of X, mu I minus I of Y, Z. And this should be 0. And here I running from 0 to infinity, and P from 0 to I. This is okay? Okay, then now here I have this equation. And now I can rewrite it. If you remember, yesterday I defined what we call a Gerstenhaber circle. If you remember, in this Gerstenhaber algebra, then here mu i's could be viewed as two quotients, which means that they are bilinear multiplications on A. And if I take f belonging to C2A to A, J as well, J, if you remember, we defined this f composed with J as or applied to X, Y, Z, because here this goes from C2 times C2 into C2 plus 2 minus 1, which means C3. Then it applies to 3 elements, and this is defined to be f of G. F of G X Y Z minus F of X G Y Z. You remember this? This is what we define this in this Gerstenhaber, in this Gerstenhaber algebra, Gerstenhaber circle as like this. Then if I view this mu i's as two quotients, I can rewrite the previous equation as a sum, again a double sum from 0 to infinity, P from 0 to I of T to P. Yeah, I'm sorry, but here P, I did a mistake here. This P goes from 0 to infinity, and it's I. Sorry, please correct it. And I goes from 0 to P. Yeah, this was better. Okay. Then here P goes from 0 to infinity, and I from 0 to P. Yeah, this is and to T to P, and here it can write it as mu I composed with this Gerstenhaber circle, mu P minus I. Okay, I can forget about X and Y, etc. And this is okay. I can rewrite them. Doesn't matter. Okay, I don't need equals 0. Then this is now call it double star, and this is equivalent to this is again my deformation equation. Okay. And now I would like to check what happened. What we have here. Sorry. what we have here is a formal power series, and it should be equal to 0 for any values of t. And now this is true if any coefficient of t to p should be 0. Then in fact this equation is equivalent to an infinite system, and we should have it. Then this is equivalent to mu. The coefficient here is mu I composite, not composite, but Gerstenhaber circle, mu of p minus I equals, sorry, and this is a sum from I running from 0 to p, and this should be 0 for any p taking the values 0, 1, 2, 3, etc. Then we have here an infinite system of equations involving this my unknowns, this mu i's. Is it clear? Now we can check. We can look at the first equations. What happened if for p equals 0, p equals 1, etc. What about p equals 0? If p equals 0, and this equation is a sum from 0 to 0, and which means that I should have mu 0 composed, not Gerstenhaber circle, mu 0, this is 0. And I told you yesterday that this, when you have this equals 0, this means that mu 0 is associative. Mu 0 is associative. This is exactly the associativity condition. And mu 0 as associative, this is true, because we started with an associative algebra, A mu 0. Then this first equation is satisfied anyway. Okay. Now let us look at the second equation here. The second equation is for p equals 1. And for p equals 1, I have a sum from 0 to 1. In fact, here, the two terms, we have only two terms. The first term is when I is 0, and p here, of course, is always 1. Then the I is 0, this is mu 0, Gerstenhaber circle, mu 1, and plus mu 1, I is 1, then this is mu 1, Gerstenhaber circle, mu 0 equals 0. Okay. And what about now? We have a condition on the mu 1 to be this first term of the mu 1. Mind you that this mu 1, this is the first term in my deformation. Remember well, my deformation is here. Oops. This is my deformation, and this mu 1 is this first term. Okay. In fact, this mu 1 is called infinitesimal. This is like Taylor the expansion in which the first term corresponds to the infinitesimals or to the derivative. Okay. Now this condition we can express it in terms of cohomology. In fact, this condition, this condition, this is exactly the condition that mu1 is a true cocycle with respect to Hochschild cohomology. And in fact, this is equivalent, the condition oops, no, is equivalent to say that mu1 is a true cocycle respect to Hochschild cohomology. And this is the first main observation made by Gerstenhaber in his theory. I mean, this is a first connection between formal deformations and the cohomology of the algebra. Of course, you should have a suitable cohomology. I mean, here for associative algebra, the Hochschild cohomology I mentioned yesterday works very well and allow us to express this some of the terms, conditions on the term using this cohomology cocycles. And of course, if you are dealing with the algebra, then it should work with the Chevalier-Eilenberg cohomology. And for if you have another structure, you have you need a good cohomology or a suitable cohomology. Of course, this is also a way sometimes to construct new cohomologies controlling the deformation, but it's not always possible. I mean, for example, for alternative algebra, you discussed with Professor Duque, we can construct a two cocycle or two coboundary operators for alternative algebra. We did it once, but we are not able to provide a complete cohomology having this as a two coboundary, and it's still an open question. Okay. Then this is the first observation. In fact, then this is a general fact, and we can also state it as a theorem. And this is true if you start with a deformation where mu1, mu2, mu p minus 1 is 0. If you start with the deformation of this form, if mu t, this is mu 0 plus, for example, t to p, mu p, if you assume that mu1 is 0, mu 2 is 0, mu 3 is 0, mu p minus 1 is 0, plus t p plus 1, mu p plus 1, plus etc. And this mu t is associative, then this implies that using the same calculations I made already, this implies that this mu p should be a true cocycle. If you remember, I denoted the two cocycles like this, Z2 of A. Then here mu1 belongs to Z2AA. Then this is our first theorem in the theory. Then let mu t, in fact, what is new here, this is mu t, but A is always fixed. We have just to extend it to a formal space. Then let the mu t be a deformation, of an associative algebra A mu 0 set mu t equals sum of t to I mu I 0 to infinity, that the first then the assertion here is that the first non-zero term of mu t after mu 0, of course, the first non-zero term of mu t, of course, I mean here after mu 0, belongs is always a true cocycle. A true cocycle. Then here, of course, with respect this Hochschild homology, which means that if t here I'm assuming that t not t but mu1 equal mu2 etc. equal mu p equals 0, p minus 1 equals 0, then and mu p different from 0. This is what I mean here. Then if I have this, then mu p belongs to Z2 of AA, is a true cocycle. Okay. Then this is the first result. And now, then now if I come back to the equation, to my deformation, then of course I have now I have a necessary condition on this. Of course, I ignore anything, a lot of things about this mu2. I don't care about for the moment, but we have a necessary condition on this first term. If it's non-zero, then it should be a true cocycle. Okay, now, this is our first result. Now, maybe I can introduce some definition. Of course, the fact that we are choosing mu1 in Z2 doesn't mean then that we can, of course, we can construct a deformation starting with this mu1. But if this mu p or mu1 is a first term of a deformation, we say that this mu p is integrable. Let me now define what we call by an integrable true cocycle definition. Sorry. If a true cocycle mu p defines an associative or is the first term, maybe I should say, is the first term of an associative deformation, mu t, we say that mu p is integrable, is an integrable true cocycle, an integrable true cocycle. Okay. Then, of course, in order to check whether this true cocycle is integrable, we should look at other conditions, and you have to come back to you have to come back to this to this main system, to this main system, and check what happened. For the moment, we only checked P1 and P0 and P equals 0 and P equals 1. But of course, we have to look at the other equations. And now, in order to relate also this equation to cohomology, I suggest to consider from this sum for any P, from this sum, I separate the elements corresponding to I equals 0 and I equals P. And if it's 0, that what I will have here is mu 0 circle mu P. And if I is P, then this is mu P circle mu 0. And if I took them together, and this means that I have that this is exactly delta mu P. Okay, then for any P now, for P larger or equal to 1, we check it for 1, but for 2, for example, then this sum I from 0 to P of mu I Gerstenhaber circle mu P minus I equals 0. This is equivalent. I can write it as delta of mu P plus a sum of, now the sum runs from 1 to P minus 1, mu I circle mu P minus I equals 0. Then I can rewrite it. Now if I then here I am considering the co-boundary map D2, then this is D2, delta 2 of mu P. Then this, in order to fulfill this equation, this mu P I'm looking for example, for P equal 2, 3, etc., should satisfy delta 2 mu P. Then what I have here is delta 2 mu P. This should be equal to minus this sum from 1 to P minus 1 mu I circle mu P minus I. And this is again an important relation or an important equation. Of course, then delta 2 of mu 1 is 0, but if I write it for P equals 2, and if P equals 2, for P equals 2, I have delta 2 mu 2. This should be equal to minus I from 1 to 1. Then this is mu 1 circle mu 1. Then if I have fixed already the first term of my deformation, I have to take a mu 2 satisfying this equation. Then this mu 2 is related to the mu 1 I fixed before. Okay, then in fact, this expression, this is exactly what we call an abstraction. This is an abstraction to integrate the mu 1. I started with 1, 2 cocycle, which is mu 1 here. This mu 2, to fix this mu 2, it should be have an abstraction here. This delta 2 of mu 2 should be equal to an expression involving mu 1. And of course, if you have if you are dealing with P, general P, then delta 2 of mu P should be expressed in term of mu1 and mu P minus 1 on the previous element you fixed already. Okay. And then this abstraction. Now I can write this abstraction as, and then this is the trilinear map. Huh? Obs, I can state obs to be this sum or minus sum. Mu I circle mu P minus I from the one, sorry, from 1 to P minus 1. Huh? For P larger or equal to 2. Huh? I state this is a trilinear map, which means that it belongs to C3AA. Huh? There are trilinear maps with on A. Huh? Okay. Then now I would like to say something about these abstractions. Huh? In fact, there is also we can check. Then there are trilinear maps. We can check delta 3 of this. Huh? Then it turns out that the delta 3 of the obs is always 0. And this is based, we have one lemma which may help to prove this. We have this lemma, which is a general fact in cohomology. If F and J, if J are bilinear maps, then we can write, then we have this delta 3 of, if you remember, if I take 2 bilinear maps, then this is, I think I write maybe use better to get more space. Then delta 3 of this F Gerstenhaber circle of G, then this is a trilinear map like we have just above. And we can express this using again this Gerstenhaber bracket, and this is delta 2 of F composed with J, Gerstenhaber composition here, minus F composed with delta 2 of J. Then now I can write down. We use this and we use this lemma to show that delta 3 of obs is 0. Then this is theorem 2 here now. Then all this abstraction to integrate the first term of my deformations are 3 cocycles. Then the abstractions are 3 cocycles. Then delta 3 of obs, this is 0. Okay, and this is also an important result. Okay, then now we can discuss a little bit this relationship with cohomology. Then if H3, what happened if all 3 or H3 oh. Okay, now maybe I can just look at example. I can also introduce here the nth deformations. Of course, we can, in order to, we can fix things. Not take infinite formal power series, but only polynomials. In fact, physicists, for example, when they deform, we just consider some finite deformations. Then if mu t, if mu t, mu 0 plus t mu 1, if your deformation, we say that you have, we call it infinitesimal deformation. It's called infinitesimal deformation. Some people call it linear deformation. They prefer this infinitesimal deformation. It's related to analysis and to this Taylor expansions and so on. And now, now let us discuss this abstractions. If my mu t is mu 0 plus t mu 1 plus t square mu 2. Of course, if I have a deformation with one element of degree 1 somehow, then the conditions are delta 2 is 0. What we should have for the first case here, mu 1 should be a 2 cocycle. This is a necessary condition, as I mentioned. And the list of abstraction, I should have mu 1 composed with Gerstenhaber composition with mu 1. This should be 0, which means that mu 1 should be also associative. This is the true condition if I'm dealing with infinitesimal deformation. Now, if I'm dealing with deformations of length 2, then I can write the condition. The first one is mu 0 composed with mu 0, Gerstenhaber circle mu 0 is 0. This is satisfied. And the second condition, it should be delta 2 of mu 1. This is 0. Okay, then we have to consider our mu 1 in Z2. And then this is the general fact. And the last equation is the delta 2 mu 1, or sorry, mu 2 now. This should be equal to mu 1 circle mu 1. Okay? And this, I can rewrite it, and this is equivalent to write this as delta 2 of mu 1 this is minus 1 over 2. I can write it now. If I want to write it as using this Gerstenhaber bracket, I should say that Gerstenhaber bracket of mu 1 should be 0 and take half of it, because the Gerstenhaber bracket here is mu 1 composed with mu 1 plus mu 1 composed with mu 1. And they take half of it, and it equals 0. Okay. And here in general, we say that this is the general equation somehow of my deformations. And we say here that mu 1 is a Morel-Cartan element. Sorry, delta mu 2 here. Okay, now then this is what we call Morel-Cartan element. This is the equation, Morel-Cartan equation. Morel-Cartan. Okay, and then in order to get the integrability, this last condition ensures the integrability of mu 1. We should have delta 2 of mu 2 equals to mu 1 composed with mu 1. And Now, the next result or the corollary of this is that if H3, if H3, I mean, if this mu1, in order to get this mu1 composed with mu1, this abstraction should be a two delta 2 of mu2. What does it mean? This ups is a 2 cocycle, but it should be a 2 coboundary. Okay, it should be a 2 coboundary. That then a corollary of this. Of this, that they have to find ups equals to this, which means that that this is in the cohomology group. Then ups belongs to H3. That ups should be in H3. And any 3 cocycle is a 3 coboundary if the cohomology class is 0. Okay, then I don't know if I'm clear. Here, my abstraction is 3 cocycle, but in order to get mu1 integrable, it should be a 2 coboundaries. Then if H3, now if I assume that if H3 of AA is 0, then in this case all obstruction vanish. And every mu p in Z2 AA is integrable. Okay, and this is the second result, or a corollary of this. What I'm saying here is we have seen before that these are 3 cocycles, but in order to extend my mu1, it should be also a 2 coboundary. 2 coboundary means that it should equal to delta 2 of some mu2, and this is mu2 will help to construct my deformation here. But if I am assuming that this H3 is 0, H3 is 0 means that any 3 cocycle is a 3 coboundary. Then since it's a 3 cocycle, with this condition, it's a 3 coboundary, then I can get this mu2 in order to extend my deformation. Then in this case, we have a one-to-one correspondence between the Z2 and any elements in Z2 provide a deformation. Okay, I can do it through this condition. Okay, I have 5 minutes. Then here now I would like to discuss equivalent deformations and provide you maybe the last result. Equivalent deformation. Equivalent deformation. Then now we fix A mu0 be a associative algebra. Then we can consider 2 deformations. Let mu, I just write the deformation of the multiplication. Of course, I mean that this is over AT. Let mu t equals the sum of ti mu I. and mu dash t, a sum of ti mu dash I, two deformations of mu 0. Then here I should assume that mu 0 equals mu dash 0. Otherwise, I'm not dealing with the same operation. Huh? Okay. Then we say that they are equivalent if there exists a formal isomorphism of the form, we can call it F, T, identity plus T F1 plus T square F2, etc., where Fi's are endomorphism A, such that Ft composed with mu t, this is mu dash t composed with Ft tensor Ft. Okay. Now, okay, it becomes tricky. Now let us write down this and rewrite this condition, and this condition using the expansions of Ft and mu t. Then what we have here is this is a sum. This is a sum of I from 0 to infinity t to I Fi, composed with a sum of t to j mu j from 0 to infinity, and this is in here I will get three sums, I j k, and t to I mu dash I, composed with t to j f j tensor t to k f k. Okay. Then I have to group all these ti's. Then here I will have the double sum t to I plus j fi composed with mu j, and here I have a triple sum I j k t to I plus j plus k of mu dash I, composed with f j tensor fk. And now let us look at this equation and see what happened with t equals 0. With t equals 0, then I have f0, then f0 composed with mu j. This is equal to mu dash, no, 0. Mu dash 0 composed with f0 tensor f0. But since f0 is the identity, this is satisfied. Now, what about t1? And t1, this is f0 composition. Here it's the composition, not the Gerstenhaber circle. You have to be careful. Composed with mu, the sum should be 1. Then this is mu1 plus f1 composed with mu 0. Okay. And here we have three terms. Mu1 composed with f0, f0, f0 is the identity. In fact, I can remove this f0 because this is the identity. Then mu 0 plus f1 mu 0 plus mu 0 composed with f0, f0, tensor f0, plus mu 0 dash f1 tensor F0 plus mu 0 dash composed with F0 tensor F1. Huh? And here we have a relationship between mu1s. Huh? Then mu1, this is mu1 dash plus mu0 dash composed with F1 tensor F0 plus mu0 dash composed with F0 tensor F1, like this, minus F1 mu0. Huh? Okay, and this is exactly delta 1 of F1. Huh? In fact, what we have here is that mu1, this is mu1 dash plus delta 1 F1, huh? Which means that these two cocycles belong to the same cohomology class. Huh? Here, the mu1 and mu dash are in the same. Allow me only 1 minute. I will make my conclusion. The same cohomology class. Hmm? And the theorem here, in fact, we proved a very deep theorem. From the theorem here says that, in fact, if you take another element, you have your two cocycle, which defines a deformation. But if you take another two cocycle, which is in the same cohomology class as your first two cocycle, you get an equivalent deformation. This means that the formal deformation depends, the integrability of mu1, in fact, depends only on its cohomology class. The integrability of mu1 or mu p depends, depends only on its cohomology class. Okay. Then if you take another element in the cohomology class, you get equivalent deformation. I stop here. Thank you very much. I'm sorry for taking this.
So let's thank the speaker. Are there any questions or comments?
Does it mean everything is clear?
Yeah. So let's thank the speaker again. Thank you, Professor.